Good evening. Welcome to the final lecture in the Exploring Space series made possible by generous. My name is Space Curator. Whether you're here in person, thank you for joining us. The theme for this year's series is Eyes on Earth. 3 lectures presented over explored access, given us new vantage from which to learn about our. We've also heard personal stories, inclusive enterprise. And we've seen how remote sensors helped us. Tonight's talk is a little different. We've so far focused on looking down at Earth, but now we're going to turn our gaze out towards other orbiting other to exoplanets. Using ground and space-based discovered, they've shown us that there's a greater diversity of galaxies than what we find in our solar system alone. And the descriptions of some of these planets, based on the data collected by astronomers and astrophysicists, sound like they could have been taken straight out of science fiction stories. What do these faraway planets tell us about our own home world, about the evolution of stars and planetary systems, about the likelihood of finding other worlds like Earth that are habitable or even inhabited? Tonight, we will hear from Dr. Nicole Colon, astrophysicist at NASA's Goddard Space Flight Center and deputy project scientist for exoplanet science for the new James Webb Space Telescope. Dr. Colon received her BS in physics with a minor in mathematics from the College of New Jersey in 2007, where she held a National Hispanic Merit Scholarship. She then obtained her master's degree in 2009 and her PhD in 2012 in astronomy from the University of Florida, winning a graduate research fellowship from the National Science Foundation. Dr. Colon has previously hunted exoplanets as a support scientist on the Kepler and K2 missions, as well as Kepler's successor, the Transiting Exoplanet Survey Satellite, TESS. For TESS, she was the director of the mission's Science Support Center, and she also previously served as the Deputy Operations Project Scientist for the Hubble Space Telescope. So not only does Dr. Colon discover exoplanets, she uses optical and infrared data collected during exoplanet transits to study the atmospheric composition and dynamics of faraway worlds. She specializes in extreme exoplanets that are unlike the ones in our solar system, using what she learns about them to gain insight into their formation and evolution. Tonight, she'll be telling us about Earth, exoplanets, and everything in between. Please help me welcome to the stage Dr. Nicole Colon.
Thank you so much for that kind introduction. I very much appreciate it, and I'm very excited to be here with you all today. So I titled my talk, Earth, Exoplanets, and Everything in Between. It would take way longer than the time we have here to tell you about everything in between. But I will do my best to talk about some of these things as we move forward to talking about what we know about exoplanets, these distant planets that orbit far away from our solar system, and as we talk about how they connect back to our own Earth. So at the very top level, we want to know answers to several questions. We have a lot of questions we've already answered, but there's some big questions still at play here as we're studying exoplanets. And some of these include, just generally speaking, how do planets form in the first place? We know of 8 major planets in our solar system, and we know of a bunch of smaller bodies, asteroids, comets, objects like that. How do planets form when they're around other stars different than the sun? That's an open question. What is the composition of exoplanets and also their atmospheres? What atmospheres do they have that might potentially support life? Are they anything like those atmospheres, again, that we can study very well in our own solar system? In addition, how does the type of star a planet orbits affect the planet's evolution? We have a very specific type of star. It's called a G-type star, the sun, and it has a certain temperature, but it also has activity. There's stellar flares, there's star spots, and the thing is, there's other stars out there that are more active than our sun. So if there are planets around more active stars, how does that affect their atmospheres and the evolution of those planets? And the bottom line, I think that a lot of people are interested in is the last bullet here. Are Earth-like planets common or rare? Again, we know of one Earth. We have one bona fide example of where life exists, and that's this planet here. So what can we say about all the other planets we're finding out in the galaxy? Are they anything like Earth? So there's two approaches to take here when talking about connecting Earth and exoplanets. And first is that we have to discover the planets that we want to study in the first place. So that's the first part of the talk I'm going to get into, and then I'll talk towards the second half about characterization. So how do we study the properties of those planets in more detail, in particular the atmospheres? So my introduction included mention of the transit technique, and this is actually the, it's the most successful, let's say, method so far to find exoplanets. So this is a technique where we're actually not taking a picture of a planet itself, but instead what we're doing is we're measuring the starlight, the brightness. We look at it as a function of time. We just take a bunch of images of a star, and we look for dips in that brightness. And if you have a planet orbiting around a star, and it happens to cross in front of the star, it causes a dip in brightness, like shown in the animation here. So if you take this same concept, so we can use this to find a bunch of planets this way, and we have found thousands of planets this way. If you take that same concept and you then dissect the light, break it down into a spectral fingerprint, as we say, you kind of split up the rainbow, imagine a prism. You make a rainbow of light when you're looking at the same planet that's transiting its star. You can actually tell what's in the atmosphere because you'll see, let's say, water's in the atmosphere. That makes the dip that we measure a certain depth. And then if something else is in the atmosphere, like methane, there's a different depth that you would see. So that's what that animation was showing. So the transit method is a really powerful technique to study planets and their atmospheres, even though we're not technically detecting the planet itself. However, I do have to mention the second most common way to study exoplanets is called the Doppler method, because with the previous method, the transit method, we can actually back out the size of the planet in addition to the atmosphere. We see how much light is blocked. We can back out the size based on the area of the light that is blocked. With the Doppler method, it's similar to how you're walking down the street and there's an ambulance driving by, and it gets louder and louder and louder as it approaches you, and then as it drives further away, it gets quieter. That's the sound waves coming towards you and away from you. It's a similar effect here where with the Doppler method, we are finding exoplanets, and actually we're able to measure their masses this way because we're detecting how the star and planet interact, and that changes, again, that spectral fingerprint that I mentioned earlier of the rainbow of light. We can see how that shifts and stretches and expands as the planet orbits around the star. So these are two of the most common methods to find exoplanets, and this is what you're going to see here on this chart. Well, it's actually animation. So with those two methods, we found thousands of planets. However, there are actually several other methods that I don't have time to go into today to find exoplanets. But what you'll see is that over the past 20 plus years, 30 plus years, we have found over 5,000 exoplanets. And so the year is shown on the bottom here, the discovery year. And so there's actually some early discoveries that were around different types of stars. And then 1995, there was the first Jupiter mass planet found around what's called a normal sun-like star. And that actually just won a Nobel Prize recently for that discovery. So 2 physicists won that award. But as you see, we march along in time, that red curve jumps up because most of the planets were detected with the Doppler method until the Kepler mission launched. And Kepler, those green bars show how transits just took over the discovery space. And so the Kepler mission really enabled thousands of planets to be discovered. And I note here that the numbers are different. This graphic's a little older than the actual planet count. So, but it's still representative of how the pace of planet discovery has also continued in great part to missions. And again, there's all these different methods to find planets that are shown here, but I just want to emphasize that we now have 5,000. And what does that mean? What have we learned from this? And this is kind of in just one chart. What have we learned? Well, first, 5,000 planets means that on average, we can actually estimate that any star in the sky has at least one planet on average. What that means is that some don't have any planets and others have multiple. But on average, every star you might look at in the sky has one planet. So that's the first thing we learned. Secondly, we learned about the types of planets. So here, this breaks down the different types of planets that we found so far. And so you can see on the upper left, there's gas giant planets. About 30% of these that we know of the 5,000, are these like Jupiter and Saturn in our solar system. So they're really puffy, giant, gaseous planets. They can be very hot or very cold. They can have orbits very different than our solar system planets. But there's about 30% that are about that size of gas giants. Then I'm going to move to the bottom right, actually, because then you have Neptune-like planets. That's, again, about 35% or so. And these are planets that are similar in size to Neptune and Uranus in our solar system. So they're still considered gas giants, but they're kind of, well, they can also be really cold or really warm. And so these two classes, the gas giant and Neptune-like, are somewhat analogs to planets in our solar system. But then this is where it starts to get really interesting. Well, it's already interesting, but on the lower left, the super-Earths. 30% of planets are considered to be super-Earths, 31%. What is a super-Earth? This is something that is between the Earth and Neptune. And as it says in the text here, these planets don't exist in our solar system. So we're finding 31% of exoplanets out there in our galaxy, because almost all of these, except maybe one, are in our galaxy. They are all not in our solar system. So it's very strange that we find so many planets that aren't representative of our solar system. And then you go up to the upper right, you get terrestrial planets. These are like our Mercury, Venus, Earth, Mars. We have 4 planets in our solar system that are around the size of Earth or smaller. And yet only 4% of planets that we found so far are this size. Now, the caveat here is that it's really hard to find small planets. So it doesn't mean that there's not more small planets out there. It just means, A, it's really hard to find them. But B, that doesn't explain why we have so many super-Earths, because super-Earths are also small, relatively speaking, but we found so many of them. So the fact that our solar system is lacking super-Earth-sized planets, that's a very big open question. So that's a real quick rundown of what the 5,000 exoplanets we've discovered so far have told us. But I wanted to dive in a little deeper to some of the current missions that are continuing to discover exoplanets and looking to study their atmospheres. And so the Kepler mission was mentioned very briefly. I didn't do it justice. I won't do it justice here tonight, but it launched in 2009 and it discovered thousands of planets using the transit method. And it really was the mission that told us that planets are extremely common in the galaxy. And we can surmise, therefore, they're extremely common in the universe. But TESS came along about 9 years after Kepler launched in 2018. And TESS is a transiting exoplanet survey satellite. And what its mission was to search for small planets around the closest stars that are quote unquote easy to study. So what that means is we wanted to look at the closest stars to search for planets, but we wanted to do that so that we could follow them up and be able to study their atmospheres very easily. Kepler found a lot of planets, but Kepler, as I'll show later, it looked at one part of the sky for 4 years. TESS is looking all around the sky, but at the closest stars. So they have very different parameter spaces. And so TESS is able to look at huge chunks of the sky all at once. This is an animation showing how it operates. So it has 4 cameras on it, actually. So they cover this huge range of sky all at a single time. And so it stares at a certain part of the sky for 27 days, and then it keeps checking through until it kind of covers the entire celestial hemisphere. So with this method, it's able to look and take images for 27 days at a time so that we can find planets. And this is actually, these are real images from the TESS mission, that it's a mosaic of all the data it took over its 2-year initial mission. And so you can actually see in these images, on the left, the southern hemisphere, that shows the band of the Milky Way kind of towards the top, and then in the north it's kind of on the bottom there. And then there's some actually galaxies in the image too. What you can't see so well on the screen though is that there's millions and millions and millions of stars in these images too. And those stars are what TESS is looking at to find planets. And I'll talk a little bit about what TESS has discovered next, but I want to point out, so it had a 2-year, what we call prime mission to operate, and it succeeded very well. But TESS has actually just recently been extended to continue scanning the sky. So it will continue operating through at least 2025. So it will continue contributing to exoplanet discoveries. So this is a diagram showing, or a schematic kind of showing what TESS has found. And the key point here is looking at the swath of orange points. So don't worry about the differences between points so much. But TESS discoveries are shown in orange. And what that's telling you, since they're all shifted to the left, that's actually telling you that TESS is doing its job, because what shifted to the left means, compared to the blue points, is that the planets it's discovering are around some of the closest stars. And also, the vertical scale here is showing planet size. And you can see the numbers 1, 2, 3, 4. Well, 1 here is the size of Earth. So if you kind of follow the horizontal line there from 1, you see that there's several orange points that cross that line, and honestly across into the blue as well, that are around the size of Earth. But the blue points are all stars that orbit further away. So they're fainter, they're harder to study, to follow up, to characterize further. So TESS has done an excellent job of doing what it was supposed to do, which was to find planets around the closest stars. So that swath of orange points, finding small planets around nearby stars. So what does that mean? What are some examples of discoveries? I, again, could spend a whole lecture just talking about TESS discoveries. This is a snapshot of some news highlights that have come out from all the things, some of the things, I should say, that TESS has discovered so far. And so there's all types of planets. It's not just finding small planets around nearby stars, actually. TESS is also finding giant planets. It's finding planets that orbit 2 stars. There's in the upper left, you can see, Tatooine has nothing on, these 97 star systems that TESS found, because TESS is finding planets around stars there's like 2 stars, just like Tatooine in Star Wars. And then there's finding planets that are as dense as a marshmallow. So it's finding a lot of interesting things. But what I wanted to call out today were 2 examples of Earth-sized planets, because TESS is helping us get to where we want to go in terms of finding these Earth-sized planets that we can study and compare to our solar system. So this is one example, the L9859 system, which at the very top graphic shows These are schematics. These planets were discovered by transit. We don't have actual images of them, so this is the best representation we can do based on the data we have. But you can see there's a schematic of Mars and Earth on the top, and then you see a little funny name, L9859. That's the name of the star. And then there's B, C, and D at the top. Those are the planets that were found in 2019, 3 planets. And you can see planet B there is between the size of Mars and Earth. And then we have 2 others that are a little bit larger than Earth. So we have, this was one of the first systems actually discovered by TESS that has these terrestrial sized planets, as we say, around the size of Earth. And we didn't discover one of them around the star, not 2, but we discovered 3 around the star. And the exciting thing though was that we weren't done, because 2 more planets were discovered in 2021, and that's what the bottom graphic shows, where the very bottom panel is showing you the solar system, again showing Mercury, Venus, and Earth for scale, and their temperatures. And then the middle panel is showing those same 3 planets, we call them B, C, D, and then on the outskirts we have 2 more planets, E and F, and they're also estimated to be about the size or a little bit larger than Earth. So this is really, well, this was one of the first exciting examples of showing that TESS can discover Earth-sized planets, and it's around a nearby star. The star is about 35 light years away, so it's relatively close, all things considered. But beyond that, people have already started to characterize these. I jumped ahead of myself here with the text on the slide, but there's observations from telescopes like the Hubble Space Telescope that are already looking to see if they have an atmosphere. And if they have an atmosphere that we can detect, what is it made of, right? So what can we say about the atmospheres of these planets? Again, are they anything at all like our terrestrial planets in any way? And I'll talk about the James Webb Space Telescope shortly. But this is the other system I wanted to highlight here that was discovered actually in 2020 by TESS. And this one was also containing Earth-sized planets, but it contained one, the first discovery from TESS, that was in the so-called habitable zone. So there's this graphic on the right here that shows a green swath, and that there's a planet D that orbits around its star, and it falls in that green swath. What that green region is telling you, it's where we've calculated that the temperature of the planet at that distance from the star, it's not too cold and it's not too hot, it's just right for life. And this is one example of a planet in a habitable zone that we know of. We know the size of the planet, and we're working on measuring the mass of the planet. We know it has a temperature that is conducive to life. It's similar to a temperature that Earth has. What we don't yet know for planet D here is if it has an atmosphere exactly or anything at all like Earth's, if it has water in it, because again, we think water is essential for life. But this is again a great discovery because it's around a relatively nearby and bright star that we can study in further detail. And then not to mention, so there are additional planets here that I didn't talk about, but they are orbiting much closer to their star, so the planets B and C there. And they are, because they're orbiting closer, they are much warmer. So probably too warm for life, but they are still around Earth size. So it's one of these systems that, or another one of these systems that is really showing us the value of TESS. And on the left-hand side, I'm not going to talk about this too much, it's kind of all on the same graphic on the right here, but the left-hand side does show the solar system in the one panel there for reference, and then this planetary system, TOI 700, is shown again for reference on the third line down there. And the interesting thing is that we also are still not done with the system, because not shown on this chart is that there was a fourth planet discovered as well, and again around the size of Earth or a little bit larger. So these systems just keep on giving even after we've started discovering planets. And there's no surprise here. You know, this has 3, now 4 planets. The other one has 3, and then it was discovered to have 5 planets. This is not a surprise because we know of 8 planets in our solar system, right? So again, finding planets with, or stars with multiple planets is not a surprise whatsoever. So this is really just scratching the surface briefly of what we've discovered, because this graphic here is showing you a representation of what we think our galaxy looks like. And in the middle there, you see the three colors shooting out. The Kepler Space Telescope that I talked about briefly, that has discovered the most planets so far, that's that green arrow there. That most of those planets are around stars that are faint and far away, compared to that red circle in the middle, which is where TESS is looking. So you can see the difference. TESS is looking very nearby. I don't even have time to talk about other telescopes that are hunting for planets. There's many, many, many more. One of them upcoming is the Roman Space Telescope led by NASA, and that has the blue curve there, or blue swath, and that's actually pointing towards the center of our galaxy, and it's going to do a very deep survey, and it's predicted to find over 100,000 exoplanets. So we only know of 5,000 right now. Roman is predicted to add to that, in an astronomical way. So we've only scratched the surface to do our demographic studies. But we already, even with only our 5,000, right, we have several Earth-like exoplanets. And so that's where characterizing them comes into play. And this is where, let's see, I think this movie will play. This is where we also have to consider stars when we're thinking about how we characterize planets and study their atmospheres. I should have shown this movie first, actually, because it shows Mercury passing in front of the sun at different wavelengths of light. So this is the sun as how we might see it normally. And you can see this is what happens when a planet transits its star, is technically some of the light is blocked by the planet. Mercury is very tiny compared to the sun, so it's hard to imagine decreasing the light, but our telescopes are sensitive enough to detect that decrease. But on top of that, the sun, in reality, at these different wavelengths, is very active. It has solar flares and spots and faculae and just features that are larger than even the planet Mercury here, as you can see. So when we're trying to study these planets via transit from so far away, we do have to take the star into account, because stars, like the sun, can be very active. And so that's something we have to consider. And the stars also provide heat. They provide flux, and that affects the atmosphere of a planet. So this diagram is just showing you all the things that we consider when we're talking about how do we understand planets, because Earth has an atmosphere, right? And there's clouds in the atmosphere, there's layers in the atmosphere, there can be atmospheric escape. So gaseous material flowing away from the atmosphere. Imagine even like a comet, how gas can blow off of a comet. So there's all of these effects that happen in an atmosphere, but the point is we can study these. Even though these planets are relatively far away, even though the stars are active, we can study them. And what do we get from this? So again, this is just one example briefly of what we can get when we study exoplanet atmospheres. So if you just look at the yellow points on this schematic here, the yellow points are real data from the Hubble Space Telescope, mostly on the left. And then there's two more yellow points on the right there that are from the Spitzer Space Telescope, which Hubble operated, or is still operating, I should say. It's been up in space for over 30 years, and it's still going strong, but it operates mostly in the visible light, the light that you and I can see. The Spitzer Space Telescope is an infrared telescope, so it looks at light that we cannot see with our human eyes, but it's looking at infrared, kind of thermal heat light. But you might notice, okay, there's a lot of things going on here, but we can actually tell from all those wiggles in the yellow points what is in the atmosphere. And so there's all these features marked, H2O being water, and then we have CO2 marked also on the right there, especially carbon dioxide. But that's based on 2 data points from the Spitzer telescope. Now we're at the point when the James Webb Space Telescope has just launched in December, just over 6 months ago. And the James Webb Space Telescope actually operates at these wavelength ranges, starting around the 0.5, 0.6 marker there on the horizontal scale. And it's able to cover way out into the infrared, farther than the Spitzer Space Telescope could cover at this time. Well, Spitzer actually retired, so it's no longer operating, so we can't use it anymore. But the Webb telescope will provide us with exquisite data so that we can see all these bumps and wiggles in great detail. And it's going to do this for some of these Earth-sized planets. So the Webb telescope is, as I mentioned, it launched about 6 months ago. And in brief, it is an extremely powerful, extremely sensitive telescope because it's 6.5 meters in diameter. That's the size of its mirror, which is about 21 feet for reference. And there's a schematic of the Webb telescope on the right. And that bottom part of the telescope, there's like 5 layers of shiny material. It's actually a sun shield, like an umbrella to keep the telescope cool. That thing is about the size of a tennis court, so just to give you perspective of how large this telescope is. And it's fully launched in space, it's fully deployed, it's fully operational essentially. They're just checking off a couple final boxes of testing. And July 12th, coming up very shortly, the first real full color images will be released, and these will be representative of the types of data that this telescope will provide us for the next 10 plus years, possibly 20 years. So this telescope is just beginning its journey, so I don't have real data to show you yet. There is a spoiler, which is now a little bit, it's public. I couldn't say this before today, but one of the first images released on July 12th will actually involve an exoplanet. So that was not previously announced before today. And so it's actually going to show us one of those diagrams like I showed on the previous slide that is a spectrum of the planet's atmosphere where we can see bumps and wiggles and see what the atmosphere is made of. What I can show you though, these are actually images from Webb. And what I can show you is, well, these are considered engineering grade images, but the point is this was just demonstrating, A, everything turns on, it works, we're getting exquisite detail that we haven't seen before. Honestly, the telescope is exceeding all its requirements, so we could predict before it launched what we could see from, say, exoplanet atmospheres, but now we know it's actually going to do even better than what we predicted. So these are just some of the early images, a very much kind of a little bit of a teaser for the July 12th release. But what we'll actually get with Webb, again, this is showing comparison to Hubble. Hubble has been an extremely powerful telescope for us in our study of exoplanets. Technically, Hubble was launched at a time when we really didn't know there were exoplanets. Hubble launched in 1990, but scientists had made the most of Hubble to look for atmospheric features and molecules, again, water, oxygen-bearing molecules, methane, things like that. And the James Webb Space Telescope is similarly going to do that, but pushing, as you can see with the arrows there, it pushes way further at these long infrared wavelengths where we can get and observe the strongest features due to water and methane and carbon dioxide. And I keep name dropping these molecules, but the reason I'm doing that is because actually such molecules, they have carbon, oxygen, water, hydrogen. They're considered some of the basic building blocks of life. So the more we understand about exoplanets and how much of these molecules are in their atmospheres, the more we can understand how common they are found, these molecules, how common they are throughout the galaxy. And then we can postulate and extrapolate to how common they are in the universe and what that might mean, again, for potential for life to form on exoplanets. And so this slide is a recap, I guess, of what the James Webb Space Telescope will do in its first year of science. Again, it's just about finishing up all the testing and everything to get it ready for science. So I don't have, real exoplanet data to show you yet. But the exciting thing is that around 70 different of these transiting exoplanets will be observed by this telescope. in the first year of science alone. So we're going to be able to measure their atmospheres using the transit method. And around 31 or so of these are Earth-sized planets. So they are just a couple times around the size of Earth or about the size of Earth. And one of the best known examples of planets in this size range is from the TRAPPIST-1 system, which is shown in the graphic on the bottom left. And this is a system that actually has 7 planets that are around the size of Earth, and every single one of those will be observed by the James Webb Space Telescope in the first year of science, and certainly beyond that. We'll just keep collecting data because this is one of the most fascinating systems we've ever found. There's 7 potentially rocky planets around a really small star, and what the schematic is showing is that the entire TRAPPIST-1 system actually fits way within the orbit of Mercury around our sun. So it takes Mercury 88 days to go around our sun. This entire star system with 7 planets fits way inside of that. So it's a very compact system. But you see that green region there, that's that habitable zone again. So that's showing you where there's a few planets in the TRAPPIST-1 system around E, F, and G that have the right temperature to be a similar temperature as our own Earth. So if they're around the same temperature of Earth and around the same size, now we have to figure out if their atmospheres are anything like Earth. And that's what the James Webb Space Telescope will be able to contribute to. So I very much am looking forward to seeing what the data provides us, in the coming years. It'll all just be coming very soon. And then as one last fun thing, on the right there, there's other types of planets too that have been found. One of these is called 55 Cancri E, and this is a fun little poster about it, but it's one of these super Earth-sized planets that is extremely hot, and it might have a lava-like surface. So it's just hot enough that it has potentially an ocean of lava, and this is something that we can study. Definitely not habitable in any way, definitely not going to have life, at least not life as we know it, on it. But it's just one of these really fun systems that we can also study that has been discovered. And neither of these systems were discovered by TESS, but as I mentioned before, there's a lot of TESS discoveries that are also going to be observed by the James Webb Space Telescope, a lot of those small planets that TESS has discovered around nearby stars. So when you put all those discoveries together, we're going to be getting a lot of great information in the very near future. So this brings me, just to the end here about connecting Earth and exoplanets. We talked a bit about discovery, a bit about characterization, and these two things, play hand in hand. We have to discover the planets that we want to study, of course, and we've already discovered many Earth-sized planets, so now we need to push further and further to study them. And the James Webb Space Telescope is really going to be pushing our forefront of our knowledge here about what we know about these atmospheres, because it is the largest space telescope we ever launched. It's the most powerful, the most sensitive. Imagine the atmosphere around an Earth-sized planet. The atmospheres are very thin. We're light years and light years away from these planets, but we can still have the sensitivity to start diving into them and say, firstly, do they have an atmosphere? What is the atmosphere made of? Is it anything like Earth? All of these questions, the James Webb Space Telescope will really start helping us push so that we can continue even beyond that and thinking about future telescopes and what else we need to do to continue our search for life in the universe. Is there anything like life on Earth? That's an open question, but I think there has to be, given just sheer numbers and statistics of, as I mentioned before, every star on average has one planet. There's billions of stars. There must be billions of planets. Some fraction of those fall in this habitable zone, and some fraction of those will be able to support some type of life. And the more we study and look for these carbon and oxygen and hydrogen-bearing molecules with current telescopes, the more we'll be able to get closer to answering that question. So I think with that, I will thank you so much for your attention and your time. And thank you for listening.
Thank you so much, Dr. Colon, for a wonderful talk. We're going to do question and answers now. We're going to be taking questions from our online audience, which will come to me. And we'll also be taking questions from our in-person audience. So if you have a question and you're here in the audience, you'll see that there's a microphone right here behind the center aisle. So make your way to that microphone, and while you do, I'll ask the first question from our online audience. So, are some stellar classifications so unstable, i.e. with flares, as you discussed, that they're hostile to life that would otherwise be in a habitable zone?
Yes, that is very much an active area of investigation. So I mentioned, even looking at that TRAPPIST-1 system, the star is so much smaller than the sun, and as it happens, the smaller the star is compared to our sun, they just happen to be more active. That's what we found in all our research. So there's a lot of flares, and so you factor in, let's say, stellar flares and energetic events like that, and the fact that the planets are much closer to their star because the stars are cooler, so the habitable zone shrinks inward. Add a flare, to a planet closer to its star, you get a potentially very inhospitable environment. Yeah.
I see we have several people lined up in the in-person audience, so why don't we take our first in-person question?
Okay. I know you're talking about some of these exoplanets orbiting the dwarf stars, and my question is, if that's the case, wouldn't these be dead planets? Because wouldn't dwarf stars have originally been, red giants, or aren't they dying stars?
Yes. Right, so there's a whole classification of stars. So I mentioned red dwarf stars and stars smaller than the sun. They're actually still considered what we call like classic main sequence stars, so they're still in the middle of their lifetime. So it is true that eventually a star like our sun will end up as a red giant and shed its outer layers, and that could destroy the planets that orbit around the star. We have seen some evidence of the remnants of those are white dwarfs. We have seen evidence of planets around white dwarfs, but they've been disintegrated essentially. So right now the dwarf stars I was talking about are just smaller than the sun, but like normal stars otherwise, although they're more active. So
Wow.
Yeah.
Great. We'll take our next question from the online audience. Is the relatively low number of terrestrial exoplanets possibly due to the limits of our detection technology?
Yes, it's extremely hard, as I mentioned, to detect a really tiny planet. I mean, I showed the transit of Mercury across the sun, and so you could see as a perspective, you're detecting signals that are like 1 part per million sometimes with these telescopes. So in some ways, it doesn't matter how big your telescope is, if you don't have the sensitivity to detect it, it's just really difficult. But that's one reason TESS is finding actually a lot of these, because it has this huge field of view, so it can observe many stars at once and look at the closest and brightest stars, so that really helps us push to find more and more small planets. So, this was our current, as of May or June, the demographics. I'm hoping that, we'll continue to see the number of small planets grow over time.
Great. Next in-person question.
Hi, I was wondering, are current models or measurements of the habitable zone based on carbon-based life, and would they need to be changed in the event that we wanted to explore alternative forms of life such as silicon-based life?
Yeah, it's, the habitable zone, there's definitely varying definitions. The most basic one is, what is the right temperature for a planet overall to have liquid water on its surface? So we're assuming liquid water is critical for life and carbon-based life. It's absolutely true. There could be life. I mean, we think about the solar system. There's Io, that's a moon, and it has volcanic plumes, and there could be extremophile life, in there as one example. That's something that we don't consider, let's say, regularly, because we kind of want to start with life as we know it, just because it's the best example we have. But people are thinking about, different types of habitable zones and what it means to have potentially different kinds of life.
Thank you. From our online audience, have you examined exoplanet type by stellar classification? And if so, are some types of exoplanets more prevalent for certain stellar classifications?
Right. So one thing I didn't mention was that, so we have our sun, right? And then we have a lot of these smaller red dwarf, M dwarf stars, we call them, that like the TRAPPIST-1 system is around. Those smaller stars are actually the most common type of stars. And we have found a lot of planets around the smaller stars. But again, there's some selection bias there because it's actually still easier to find a planet in general around a small star because the planet has a bigger effect on the small star, no matter the planet size. So there is a bias there, and so that's why we also develop missions of all types so that we can try to cover all the parameter space and see, you know, okay, what is the true demographics? And at least right now, you know, we have what we have, but it looks like planets are definitely pretty common around at least stars like the sun or smaller. Mm-hmm.
Great. From the in-person audience.
Hi, thank you so much. This has been super interesting. Actually, your answer just kind of leads up to my question, which is, how do you figure out the size of the planet? Because if you're just measuring the transitive thing and there's like the dip, you know, in brightness, how do you know it's not just like a small planet that's like really close or a big planet that's far away?
Mm. Yeah, so there's a few tricks to that too, actually, because when we detect something, let's say something in transit, you know, passing in front of a star and blocking light, it could actually also be a star, blocking star. So we have to do some measurements to check on that. And so it's literally, in a way, just a ratio of areas. So we can say the disk of a star has a certain area, and then the disk of a planet has a certain area. So you take how big the dip is, and you actually back out. There's a square root in there, and you just back out the size of the planet, because we know the size of the star through other techniques. So that's how we know the size of the planet, is we do have to estimate the size of the star somehow, and then guesstimate, okay, not guesstimate, calculate, I should say. It's robust calculations of what the size of the planet is once you have the size of the star. However, what really helps ultimately too is that Doppler method, getting a mass independently too, to prove that it's also a planet mass object. So there's a lot of things that come together when we're confirming all these 5,000 planets. But yeah, so the size, it's all about areas, honestly, and a little math.
And what about distance from the star?
Oh yeah, distance from the star. So from our perspective, you know, these planets, they all orbit stars dozens to hundreds of light years away. So actually the distance between the planet and the star doesn't affect our geometry, our calculation, because it's such a minuscule effect at the distance that those systems are from us. So yeah, we don't actually have to consider that geometry. We just know that it transits, you know, passes in front of the star, and then we can do a little math to get the size.
Great.
Yeah.
So then is there any use to calculating like planetary density or anything like that, or not?
Yeah, oh yeah, planetary density, I mean, absolutely. That is actually, that's the best of both worlds, when we can get a radius through the transit method and we get a mass through the Doppler method, combine them, get the density, and when we have the density, we call it the bulk density. We can say, okay, is the entire planet, is it kind of like the density of Earth, you know, is it rocky or is it gaseous? And then we can use that to predict the size of the atmosphere then. So it all comes together, and then we say, okay, this planet has a great density, like low enough that it should also, like apparently has a large atmosphere around it. Put it all together, use all our telescopes, tell what the atmosphere is made of. Yeah, so it honestly, every single piece interplays together.
Thank you.
Mm-hmm.
Yeah, thanks. From our online audience, do you think any of the exoplanets have any intelligent life? So speculation, what do you think?
Well, exoplanets, yes. I could talk about Earth having intelligent life. No, exoplanets, honestly, I think by sheer numbers, again, personal opinion, because we don't have the data for this yet. Personal opinion, there's a lot of Earth-sized planets. Even though there's only 4%, it's still 4% of 5,000. So enough that, you know, we're starting to get there and find planets that could potentially support life. So yeah, when you do the sheer numbers of all the things we haven't discovered yet, just because it's hard, and then you add in, you know, the likelihood of life. I mean, there's a lot that had to happen to get us here, but the universe is so big. I mean, there just has to be some type of intelligent life out there,
Great.
beyond Earth.
Another in-person question, please.
Yes, thank you. Okay. So the Earth, of course, is an oblate spheroid, i.e. essentially round. And we've looked at, with direct observation, things like Arakoth, where it basically looks like a snowman from two things that crash into each other, or, the Mars moons, which are like eggs. So my question is, are these telescopes in any fashion able to determine shape? And have we actually discovered like something that's quote unquote planet size or whatever? And conversely, because of this non-oblate spheroid shape, have any of them in their transits or anything like that caused a lenticular motion effect so that you had an illusion of it doing one thing, but then the second observation made you go, oh wait, that's different?
Yeah, okay, so the first part of your question, so the shape of the planet, it's definitely difficult to do, but with the right data quality, let's say you have a transiting planet, you can actually, normally we would see like a very smooth dip in the brightness, but if the planet is oblate in any way, elongated because of tidal interactions, maybe it orbits extremely close to its star, and so the planet is being deformed. We have seen some evidence, or there's at least a lot of predictions for it. We are starting to see some evidence of this oblateness in the light curve. So the light curve shape is skewed just enough that we can guess based on models that is what we're seeing, this oblate, shape. And these are, again, for some of these planets though that are extremely close to their stars, like orbits of days we're talking here. That's how close you have to be to see these effects. So we're seeing that. And honestly, I do think the James Webb Space Telescope will see some of that because it will have the precision and the data quality to detect, the kind of minimal or minuscule changes in the light curve that we're looking for. So we're getting there, and so we have seen a little bit of evidence so far. And then the other factor, you mentioned, I think that is also something that's really difficult to see. We often, so when we're discovering planets, we see them for many orbits at a time. Let's say TESS stares for 27 days. It can see the same planet transit its star several times. And so you can compare, the differences to see if there's any changes between the transits. But often when we use a telescope like Hubble or with the James Webb, we only look at one transit at a time. So like measuring variable changes or anything funky, is a little harder. But one thing we do with these telescopes is we propose how to use them. So as astronomers, we say, we want to study this effect. So that might make for a good proposal of something to use the telescope for, yeah.
Thank you.
Yeah.
Thanks. Another question from our online audience. What atmospheric chemical signatures could indicate photosynthesis? Is it possible to detect photosynthesis?
Well, I think technically anything's possible with the right technology. Whether we have that technology is really difficult. Well, one thing we're trying to think about is, yes, detecting signs of vegetation. So photosynthesis plays in there. One of those ways is by actually looking more at visible wavelengths to look at more oxygen, even like ozone molecules. So that's actually more prominent in visible light because that's where our photosynthesis happens on Earth. So that's something that we probably need new technology, a bigger advanced telescope in the visible for that. But that's where we would look, in the future.
Great. I think we have a few more questions in the in-person audience.
That was a great segue to my question.
Yeah.
First of all, yes, thank you so much for being here. This was great. So today you talked a lot about exoplanets within our galaxy, and you had that really great photo that showed the galaxy, and the TESS was that little red, I think we had the little yellow, and then the bigger but still relatively small blue. And then you talked about, there was another photo of, I think it was a satellite or a new telescope, and you talked about how just that little part was the size of a tennis field for scale. So my question for you is, we're making objects that are bigger than a tennis field to send up to space. Obviously, at a certain stage, we won't be able to get any bigger with what we're making, and we're still barely scratching the surface in terms of what's in our galaxy. So do we have, are you aware of any innovation, technology, thinking being done on what's next? What's like the post-satellite, post-telescope age of technology, so that way we can get a better viewpoint in our galaxy without having to just build bigger and bigger? So thank you.
Yeah, definitely a great question. One thing, about the James Webb Space Telescope, so with the whole tennis court-sized shield there to make it cool, it actually did have to launch folded up inside its rocket in order to fit and launch. So that's actually one technology that was kind of very innovative for the telescope, was how do we create a material that folds up, survives a launch, and then deploys and is secure enough to protect the telescope. So that's something that we did develop, and so people are thinking about the future telescopes might have similar technologies. So they don't necessarily have to be bigger, but if they are bigger, we know how to launch something when it's folded up now and deploy it. This was the first time we'd done it. So that's part of an answer, because technically the goal kind of is to do sometimes keep going bigger and bigger. One thing I did not talk about whatsoever are telescopes on Earth. There are many telescopes on Earth, and a lot of them are also getting bigger and bigger, to be fair, in order to just push further and further in the universe. They're like big light buckets, so the bigger your telescope, the shorter the time it takes to collect your data, and they're just can be more sensitive, more powerful. So there's a lot of things in the works right now in terms of new telescopes on Earth, and even thinking about some future telescopes in space. There's nothing yet planned bigger than the James Webb Space Telescope. So it is going to be different technology. So every telescope we launch to has more advanced technology, like newer cameras and things. So that also helps. So I'm not an engineer, so I can't speak, for sure. But I know that every new mission we do make, or even the ground-based observatories, they are always often on the leading edge of technology. And so there could be more breakthroughs so that we don't just have to go bigger and bigger. I don't have a final answer for what the answer is, but there's definitely plans, and people, engineers are amazing. Yeah. That's all I can say as a scientist. But I think give it time, and people will discover more ways to be more efficient. Maybe that's the word. Mm-hmm. Yeah.
Great. We have time for just one more question, and I see that we have a young audience member who may have a question, maybe an aspiring exoplanet scientist. Would you like to ask the last question?
Does it have to be like water, like H2O water, or can it be something like liquid methane for life to develop?
Yeah, there definitely can be other types of liquid oceans, that we're searching for. Again, we think water specifically just because we know humans thrive on it. Life as we know it thrives on liquid water. But there are moons, again, in our own solar system that have what we think, they have frozen surfaces, and then we think they have liquid oceans underneath. That's not necessarily water. So there are different ways of looking at life that, astrobiologists are looking at. There's a lot of people that work together to figure these out, and I think as we move forward, we're going to keep working more and more together to be able to answer questions, like that even better. What signs of life can we look for, considering all these factors, different types of oceans, liquid methane, liquid, anything beyond liquid water, and what that might mean for life and different types of life, and how we can make science fiction into science fact.
Right. Well, please help me thank Dr. Nicole Colon for a wonderful talk. Great. And thank you all, to our in-person audience and those watching online, for being here with us, and then also for engaging in a very fun question and answer period. I want to tell our in-person audience that we have some telescopes outside, and we have some stargazing happening. So if you want to look at the sky tonight, some of our astronomy educators will help you do that. And I want to again thank our sponsors, United Launch Alliance and Aerojet Rocketdyne, for supporting this program and making it possible. And if you want to learn more about Smithsonian's National Air and Space Museum and our upcoming public programs, please look online at our website, which is, what is it, airandspace.si.edu. I should know it. But check us out online and visit our Udvar Hazy Center and come see our downtown location here on the mall after this fall when we reopen part of the museum to the public. So thank you again.
Thank you.